So we were just talking about how electron energy, which is related to velocity, and position are complementary. So the energy of an electron, the kinetic energy, would be 1/2 times the mass times the velocity squared. So there's uncertainty in the velocity, the mass doesn't change. But in order to know the energy, we would have to know its velocity. We can't know the velocity and the position at the same time. So for an electron with a given energy, we can't tell you where it is. The best we can do is describe a region where it probably is. And that's called an orbital. It's very similar to Bohr's orbit, but orbital is not the same. This is a probability distribution map showing where an electron is likely to be found. Many of the properties of atoms are related to the energies of their electrons. So knowing something about the energy of the electrons is important. So this is Schrödinger's equation, same guy who had the cat in the box. And this looks, really deceptively simple here. This allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location. But when you solve this equation, you don't get specific numbers, you get wave functions. That's what these guys are, wave functions. And so those describe the wave-like nature of the electron. And if we graph that wave function squared, then we get the representation of an orbital. It's okay if none of that made sense. So, a lot of very smart, creative scientists, famous scientists, worked really, really hard on this stuff. Some of them, like Einstein, trying to prove that it was wrong because he didn't like it. But the calculations will show that the size of an orbital of this region, its shape, its orientation in space, are going to be determined by 3 different integers, whole numbers, that are in the wave function. And so we put those numbers into the wave function to quantize the energy of the electrons, because we know that the electrons can only have particular energies within a given atom. And so we can't have solutions here that are giving any possible energy. So there's these 3 numbers that are put in to quantize it. And these are called quantum numbers. The first one is the principal quantum number, which is lowercase n. The angular momentum quantum number, lowercase l. Magnetic quantum number, m sub l. Then there's a 4th quantum number. It's actually not an integer. It's called the spin quantum number, m sub s. And I want you to try to follow along with these letters and try to get your mind around what they mean. And then when I've thoroughly confused you, I have an analogy that somehow relates this stuff to a hotel. And I think I just need to be able to visualize things, and this gives me something to visualize that makes sense so I can understand how these quantum numbers work. So the principal quantum number is the most important one. It describes the overall size and energy of an orbital. So this is very similar to Bohr's energy levels, his orbits. There was orbit n equals 1, n equals 2, n equals 3. And as you go up in n, you get higher in energy, and it's larger in size. So what are the possible values for n? It can be any integer, any whole number that's greater than or equal to 1. 1, 2, 3, 4, 5, 6, 7, numbers like that. The bigger it is, the higher the energy, and the larger the orbital size. So for hydrogen, and for hydrogen only, the energy of an electron with principal quantum number n is given by this equation. Negative 2.18 times 10 to the minus 18th joules times 1 over that quantum number squared. So that's going to give us a negative energy. The energy is negative because the electron's energy is lowered by its interaction with the nucleus. So if you think about potential energy, right, the higher something is above a surface, the less stable it is. And the lower it gets, the more stable it is. And everything tends towards lower potential energy. You're like, well, how do you have negative potential energy? Well, that just means it went below what we defined as zero. Okay? So if you stand near the ocean and you throw a rock out towards the ocean and it goes up, its potential energy is increasing as it goes up, and then it starts to fall down, and its potential energy is increasing as it decreases in elevation, and then it hits the surface of the water and it stays there. No, it doesn't. It keeps going. Well, what's its elevation then? Negative, because it's below sea level, right? Well, why is sea level 0? Because we decided it was 0. So the energy is negative. Sorry. Another thing that as n gets larger, the energy differences between those orbitals get smaller and smaller. So this is an energy diagram. And here we're looking at these different principal quantum numbers. And this is a little bit, this is where thinking about the Bohr model. So for the Bohr model, we had these circular orbits. As you go out, the orbits get bigger and higher in energy. They also get closer together. The distance between them in energy is smaller, and the physical distance between them is smaller. And so that's what we see with the energy for the electrons. So principal, this is for hydrogen. For an electron in the n equals 1 state, this is the energy. And if we go to higher n's, the energy gets higher. It goes closer to 0. It's going up, right? It's getting a smaller negative. I know that's confusing. Second number, the angular momentum number. So this describes the shape of a molecule. This is L. It can have an integer value anywhere from 0 to 1 less than what n is. So that L equals 0, 1, 2, and 3. And we don't usually refer to them as the numbers. There are letters that we use instead. And these do have historical importance, and that's why they're not A, B, C, but they're S, P, D, and F. So when L equals 1, that's designated as S. Sorry, did I say 1? I said 1, didn't I? L equals 0 is S, 1 is P, 2 is D, and 3 is F. So what values of L are possible when n is equal to 3? So here we've got n is equal to 3, and that next number L is 0, can be 0 up to n minus 1. So if n is 3, 3 minus 1 is equal to 2. So then L can be an integer starting at 0 up to 2. So it could be 0, 1, or 2. Those are the possible values. So that would be C. 0 is S, 1 is P, 2 is D. You just got to try to stick with me here, and hopefully by the end of the lecture, it will start making a little bit of sense. I hate telling you guys about this stuff. It's like, ah. Okay, the magnetic quantum number. This determines the orientation of the orbital. Is it like pointing up and down, or is it pointing side to side? It's the direction in space. And the values for this, again, are integers. They range from whatever L is as a negative to L as a positive number, including 0. And the number of M sub L values tells us how many orbitals have that particular shape. So for L equals 2, then these M sub L values go from negative L to plus L, so they go from negative 2 to plus 2. So negative 2, negative 1, 0, plus 1, and plus 2. So there's 5 different values here. There's 5 different orbitals that share that L equals 2 number. What values of M sub L are possible for L equals 2? This is dumb because the previous slide just answered this, right? Well, let's do it different. Let's say L equals 1. The correct answer is here. So if L equals 1, then M sub L can be anywhere from negative L to positive L. Well, if L is 1, you can go from negative 1 to positive 1, and there's only one integer in the middle, that's 0. Then there's the spin quantum number. So electrons have spin. It's their fundamental property. And so it's not the same as like a Beyblade top that spins counterclockwise or clockwise. Right? Some spin one way, some spin the other way. But you can think of it that way. That'll be good enough. Okay. So this number is either plus 1/2 or minus 1/2. It indicates the orientation of the spin. We talk about it as being up, positive 1/2, or down, negative 1/2. It's like a spinning top that's either spinning clockwise or counterclockwise. Okay, there's just 2 possibilities. So to describe an orbital, we're going to have the first 3 quantum numbers are going to describe an orbital. So if we have n is equal to 1, L is 0, and M sub L is 0, that describes what we refer to as the 1s orbital. This number, 1, is that principal quantum number. S corresponds to L equals 0. So if we look at orbitals with the same value of n, we say they're in the same principal energy level or the same principal shell. And if they have n and L in common, they're said to be in the same sublevel or subshell. So here's a picture that may or may not help. So for n equals 1, this is going to be the lowest in energy, the only possible value for L is 0. And for L equals 0, we can only have M sub L equals 0, and so we have 1 orbital there. In the second level, there's 2 possibilities for L, 0 and 1. Again, for L equals 0, there's only one possibility, M sub L equals 0. This is the 2s orbital. If L equals 1, then M sub L can be negative 1 up to positive 1, and so there's 3 different orbitals here. N equals 3. We've got the 3s and the 3p. And now we've got this other possibility where L equals 2. And then M sub L can be from negative 2 to positive 2. There's just 5 different ones. List the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? So we're told that it's 5D, right? So that means that n is equal to 5. And this 5 literally is the n. And D, okay, what was D? Well, it went S, P, D, F. That was 0, 1, 2, 3. So if we've got a D orbital, that means that this number corresponds to 2. That's L. This is valid because L can be anywhere from 0 up to 1 less than 5. So 2 is fine. And then in M sub L, this can go from -2 to +2. So we can have +2, we can have +1, we have +0. 0, -1, and -2. So there's 5 different d orbitals, and so we can describe them by these numbers. So 5, 2, 2, 5, 2, 1, 5, 2, 0, 5, 2, -1, and 5, 2, -2. It's a little bit like an address or a social security number or a student ID number, right? Each student has their own number. Or if you're into cars, a vehicle identification number, different parts of that number indicate what year it was made and where it was made and the body color and this and that and the other thing. But each car has its own individual number, right? No two are exactly the same. Each set of quantum numbers is supposed to specify an orbital, but there's a mistake, and we're supposed to fix that. So here, n is equal to 3. Well, that's fine. But if n is 3, can L also be 3? No, L can only be up to 1 less than 3. Why? Because they told us. Okay, there's no good why there. So L could be 0, 1, or 2, but it can't be 3 here. So this is the one that's wrong. But before we pick what it's going to be, we have to look at the next number, M sub L. If M sub L is +2, that tells us that L equals 0 is not going to work. L equals 1 isn't going to work because then this would not be possible. So L must be 2. Here we've got n equals 2. Can L be 1? Yeah. If L is 1, can M sub L be -2? No. If L is 1, M sub L will be -1, 0, or +1. It doesn't matter which one we choose. I kind of feel like 0 today. Oh, this one. N is equal to 1, L is equal to 1. Does that work? No. What's the only possibility for L? 0. L must be 0. And then if L is 0, can M sub L be 0? Sure. So there's questions like this in the homework and in the worksheets. And I don't anticipate putting anything like that on an exam because I don't think it's that important. So how does this explain atomic spectroscopy, those spectra that we see? Each wavelength in the atomic spectrum corresponds to a particular electron transition between orbitals. The electron's moving from one orbital to another, And that's going to be a difference in energy. When the atom absorbs energy, the electron gets excited. The electron gets energy, gets excited, goes to a higher energy level. It's not stable. Can we stay excited all the time? No, we run, it's not sustainable, right? It's fun to be excited, but you can't be that way all the time. So it gets excited, it can be that way for a while, but then it'll always come back to a lower energy state. And when it does that, it's going down in energy. That energy has to go somewhere. The energy gets emitted as a photon of light. That energy is going to be equal to the energy difference between the orbitals. So we can look at the energy or the wavelengths and the energy of the light that's being absorbed and emitted when electrons move, and we can calculate the difference in the energy levels. So if we have an electron in the first principal energy level and it absorbs a bunch of energy, it could get excited to, say, the n equals 3 level. This is going to be higher in energy. It's not going to be stable up there. And so at some point it's going to relax or fall back down. It could fall down to n equals 2. It could fall all the way to n equals 1. If it falls to n equals 2, the difference in energy here gets released as light. And that's the light that we can see. Any questions? For an electron to go from a lower energy state to a higher energy state, it has to get the exact right amount of energy. It's like riding on a bus where they only take the exact fare. It's $1.25, maybe. And you're like, well, I don't have $1.25. Can I pay you $2? And the bus drivers, no. It has to be exact change. It has to be exactly the right. And you're like, man, this is so stupid. I'm giving you extra. They won't let you ride. It used to be a thing. So if the electron is getting too much energy, it's just going to say, sorry, got to pass. I can't use that. It has to have the exact right amount of energy to jump from that quantum leap from one to another. So electrons in the higher energy states are unstable. They'll lose energy and go back down. Every line in the emission spectrum corresponds to the difference in energy between two different energy states in that atom. Well, hydrogen is a simple atom. It has one proton and only one electron. And so we can actually predict and do some calculations with hydrogen that are impossible for other more complicated atoms. The wavelengths of the lines in the emission spectra of hydrogen can be predicted by calculating the difference in energy between any two states. So for an electron in some energy state n, there's n minus 1 states that it can transition to, meaning come down to. So both the Bohr and the quantum mechanical models can predict those lines very accurately for hydrogen, for one electron. So these are the calculations that can be done with hydrogen. So you're looking at the change in energy. The energy of the photon that gets released is the difference in energy between the two levels. So it's the final energy minus the initial energy. Well, we learned earlier that the energy of an electron in hydrogen is minus 2.18 times 10 to the minus 18th joules times 1 over whatever n is squared. So this will be the final energy, and we're subtracting the initial energy. And then we can simplify that a little bit and get this expression here. And so this is one that we will use occasionally. And then these are other important ideas. So the energy of the atom is the negative of the energy of the photon. So the energy of the photon is positive because the atom lost that energy. Okay? And the wavelength of the light is related to the energy using this equation. Again, we've got Planck's constant and the speed of light. So these are the lines that we see for hydrogen. These are the ones in the visible spectrum. There's kind of purple line and sort of this aquamarine and red. And those correspond to transitions from n equals 5 to 2, and 4 to 2, and 3 to 2. There are other transitions that occur, but these that are going to n equals 3 are higher in energy, and we can't see them with our eyes. I'm sorry, they're lower in energy, longer in wavelength. And we can't see them with our eyes, but those are infrared. And then these transitions are higher in energy, shorter in wavelength, and those fall into the ultraviolet region. Also cannot be seen with our eyes. So these are the only three that we can see. So this is a question that could be on an exam. Which transition emits light with the shortest wavelength? Well, I guess that would work, but it's not what I meant. Which one looks more energetic? The bottom one. So this one's higher in energy. Is high energy a long wavelength? Long wavelength, sorry, or a short wavelength? Short. So high energy, short wavelength. Lower energy, long wavelength. So you draw two waves, and one of them's kind of drawn out, and the other one's really bouncy. And that one looks more energetic. It is. It's higher in energy. And then you just compare. Oh, well, look at that. This wavelength is longer, right? That's longer. That goes with low energy. So here, when they're saying the shortest wavelength, the short wavelength is going to be higher energy. So we're looking for higher energy. So this is 5 to 4, 4 to 3, 3 to 2. As n gets bigger, the distance between them gets smaller, right? So we've got this transition up there, which is so small I can hardly write in it. We've got this one, and we've got this one. The distance is related to the energy. Which one's higher in energy? C, this one from 3 to 2. That's a bigger energy change. Higher energy is a shorter wavelength. They're asking for the shortest wavelength. Determine the wavelength of light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. We've got n equals 7, we've got n equals 2, and this is asking us for the wavelength. So we have two n's. We have an initial and a final. Which is the first one? It goes from 2 to 7. So 2 is the initial, and 7 is the final. And then we have that equation. think it's minus 18. Right? I don't expect you to memorize that. Can anybody confirm, did I get that exponent right? Is it 18 or is it 19? 18? Phew. Okay, so let's just plug these numbers in here. So the final is 7. 7 squared is 49, right? 7 times 7? Minus 1 over 2 squared, which is 4. Now, don't do anything like trying to find the lowest common denominator and subtract those fractions and stuff. Just let your calculator do it. So I'm going to type this in as negative 2.18 EE, negative 18, times, I'm going to use parentheses, 1 divided by 49 minus 1 divided by 4. Close the parentheses, equals. Oh, I lost my negative sign? No, I didn't. That is positive. Delta E here is positive because we're talking about the energy of the atom, and it's absorbing this energy, so it's coming in. Does that answer the question? No. They want the wavelength. So the wavelength is equal to hc over E. So the wavelength is going to be Planck's constant times the speed of light. All those numbers will be given to you on an exam. Divided by the E that we just calculated. So the joules cancel out, the seconds cancel out, and we're going to end up with an answer in meters. Double check that. Oh, same number. Any questions?
I thought that H was to the 34.
Oh, well, yes, you're right. It is. 31 was the mass of the electron. I thought that looked a little weird. Thank you. Minus 34. Let's try that again. Yeah. 1, 2, 3, 4, 5, 6, 7. Thank you. Any questions? Mm-hmm.
How did we know which values the 2 and the 7 went into?
So they're giving us the 2 and the 7 here, and we have to figure out from the words which is the initial and which is the final. If you get them backwards, the only thing that's going to be different is the sign. That's the only thing that's different. Any other questions? This only works for hydrogen. Yeah.
So the 2.18 is always going to be like that?
Yeah. Yeah, and if you remember that Rydberg equation, this is related to the Rydberg equation. because that energy here is equal to hc over lambda. And the Rydberg equation was 1 over lambda and a number times 1 over m squared minus 1 over n squared.